Good morning, everyone, and welcome to today's presentation. I'm delighted to have you here. Today, we will be exploring the expertise of Dr. S.K. Singh, who holds a PhD and is a certified professional in the field of oral solid dosage manufacturing. We'll look into his qualifications and delve into the key aspects of manufacturing in this area. Over the next few slides, I'll guide you through the main topics and insights related to this specialized field. Let's get started. Let's start by understanding some key terms that are fundamental to our discussion today. First, CMA, or critical material attribute. These are the physical, chemical, biological, or microbiological properties of raw materials. They directly impact the quality, safety, and performance of the final product, so controlling these attributes is crucial. Next, we have CPP, or critical process parameters. These refer to the key variables within our manufacturing process that influence our product's quality, safety, and efficacy. Monitoring and controlling these parameters within set limits ensures the final product consistently meets its critical quality attributes, or CQAs. Speaking of CQAs, these are the properties of the finished product itself, whether physical, chemical, biological, or microbiological, that must be maintained within specific limits. Doing so guarantees the product's quality, safety, and efficacy for the end user. Now, when we look at the bigger picture, these certifications, CMA, CPP, and CQA, collectively strengthen our operations. They help us improve financial efficiency, ensure regulatory compliance, and uphold quality excellence in our oral solid dosage, or OSD, manufacturing. Finally, let's connect these concepts to our pharmaceutical unit operations. The input material attributes, which are the CMAs, influence the process parameters, the CPPs. These process parameters, in turn, affect the final product's quality attributes, the CQAs. Understanding this relationship helps us optimize our manufacturing process to consistently produce high-quality medicines. All right, let's dive into the key attributes we consider when evaluating input materials, often referred to as CMA or input material attributes. First, particle size is fundamental because it impacts how the material flows and interacts during processing. Alongside that, particle size distribution tells us how varied the sizes are within the sample, which can influence everything from mixing to compaction. We also look at fines and oversized particles. Essentially, the small particles that can affect flowability and larger particles that might cause bridging or segregation. Particle shape is another critical factor. Whether particles are spherical, elongated, or irregular shapes can significantly influence handling and processing. Density measurements, bulk, tapped, and true density, are vital because they help us understand how densely packed the material is, which affects storage and transport. Cohesive and adhesive properties are also key, as they determine how well particles stick together or to other surfaces, impacting flow and processing efficiency. Electrostatic properties shouldn't be overlooked either, since static charges can cause particles to stick or repel unexpectedly, complicating handling. Lastly, moisture content plays a crucial role. Too much moisture can lead to clumping or degradation, while too little might cause dust issues or static. All these attributes tie together to give us a comprehensive picture of the material's behavior, helping us optimize processing conditions and ensure quality throughout the production cycle. When it comes to blending or mixing in CPP, there are several key factors we need to consider to ensure quality and efficiency. First, the type and geometry of the mixer are crucial because they influence how well the materials combine. Different mixers are designed for different types of products, so choosing the right one is essential. Next, the mixer load level matters. That's how much material we put in relative to its capacity. Overloading or underloading can affect the mixing quality. The order of addition is also important. Adding ingredients in the right sequence can make a big difference in the final product's consistency. Then, we need to pay attention to the number of revolutions, which includes both the time and speed of mixing. Too fast or too long, and we might damage the material or cause uneven blending. The pattern of the agitating bar turning on and off can also influence how thoroughly everything gets mixed. Discharge method is another key point. How we remove the mixed product from the mixer can impact its quality and ease of handling. Holding time, or how long we keep the mixture in the mixer, allows for proper homogenization, especially in complex formulations. Environmental temperature and relative humidity are also important because they can affect the mixing process and the stability of the ingredients. Keeping these conditions consistent helps us achieve predictable, high-quality results. All these factors are interconnected and play a vital role in optimizing the blending process in CPP. By paying close attention to each, we can ensure our final product meets the desired specifications and quality standards. Now, let's talk about the key outputs in blending and mixing, which are crucial for ensuring product quality. First, blend uniformity is essential because it ensures that every dose contains the right amount of active ingredients, leading to consistent efficacy. Potency is another critical factor. It measures the strength of the active components in the mixture, directly impacting the therapeutic effect. Particle size and particle size distribution are also important, as they influence flow properties, dissolution rates, and stability of the final product. Density measurements, including bulk, tapped, and true density, help us understand how the powder behaves under different conditions. Moisture content is vital because excess moisture can cause stability issues or caking, while too little may affect flowability. Flow properties determine how easily powders move and process during manufacturing, and cohesive or adhesive properties affect how powders stick together or to equipment. Powder segregation is a common challenge. Different particle sizes or densities can cause separation, impacting uniformity. Lastly, electrostatic properties can lead to powders sticking or repelling, which can interfere with processing and mixing. Overall, these outputs tie directly into our goal of achieving a consistent, high-quality product through effective blending and mixing practices. Let's look at this example of blending. We see that the CMA, which is the particle size distribution, plays a key role here. Then there's the CPP, or critical process parameter, which involves mixing time and speed. And of course, the CQA, or critical quality attribute, is the blend uniformity. Now, from a scientific perspective, these points are interconnected. For instance, having a wide particle size distribution can increase the risk of segregation during blending. That's because particles of different sizes tend to separate if not mixed properly. On the other hand, improper mixing, whether it's too short, too slow, or not thorough enough, can lead to poor content uniformity. That's a critical quality attribute because it directly affects product consistency and efficacy. So, understanding these factors helps us optimize the blending process, ensuring we maintain product quality and reduce variability. It's all about controlling these variables to achieve a uniform blend every time. Now, let's take a closer look at size reduction in CMA. When we consider particle or granule size, it plays a crucial role in how the medication behaves and dissolves. Smaller particles typically enhance surface area, which can improve dissolution rates, but they may also affect flowability and stability. Hardness and plasticity are also key attributes. Harder particles tend to resist breakage, while plasticity indicates how easily particles deform without breaking. These properties influence how the granules withstand processing and handling. Viscosity, on the other hand, relates to the flow properties of the material, especially when it's in a semi-solid or liquid state. Managing viscosity is essential for ensuring proper manufacturing and consistency. Brittleness and elasticity are important mechanical properties. Brittle particles break easily, which can be useful or problematic depending on the context, while elastic materials can deform and recover their shape, impacting how they respond during processing. The solid form or polymorph refers to the different crystal arrangements a compound can have, which can significantly influence stability, solubility, and bioavailability. Granule porosity and density are also vital. They affect how tightly packed the particles are and how they interact with the environment, influencing dissolution and stability. All of these attributes are interconnected and play a fundamental role in optimizing size reduction processes, ultimately impacting the effectiveness and quality of the final pharmaceutical product. Now, let's dive into the critical process parameters, or CPP, specifically for size reduction through ribbon milling. One of the key factors here is the ribbon dimensions. The size and shape of the ribbon can significantly influence how effectively it breaks down during milling. Next, we have ribbon density, which affects the material's resistance to size reduction. Denser ribbons often require more energy to process. Along with that, ribbon porosity or solid fraction plays a crucial role. Higher porosity means the material is more porous or less dense, which can facilitate easier milling. Moving on, when we consider impact or screening mills, several parameters come into play. The type of mill itself impacts the process. Different mills are suited for different materials and desired particle sizes. The mill speed is another important factor. Higher speeds generally increase the milling efficiency, but can also lead to more heat generation or wear. Blade configuration, type, and orientation are key because they determine how the material is sheared or impact processed. Screen size and type are equally critical. They control the particle size distribution of the milled product. Lastly, the feeding rate influences throughput and consistency. Feeding too quickly or too slowly can affect the uniformity of the process. All these parameters are interconnected and must be optimized together to achieve the desired size reduction efficiently and consistently. Understanding these critical process parameters helps us control the process better and ensures we meet our product quality standards. Let's talk about size reduction output and what it really entails. First, particle or granule size is crucial because it influences how the material behaves during processing and in the final product. Understanding the particle size distribution helps us see how uniform or varied those particles are, which impacts flow and compaction. Next, particle shape plays a significant role. Whether particles are spherical, elongated, or irregular can affect flow properties and how they pack together. Speaking of which, bulk, tapped, and true density give us insights into how dense the material is in different states. Bulk density tells us about the loose packing, tapped density about compaction, and true density about the actual solid material. Flow properties are essential because they determine how easily powders move through equipment, which influences manufacturing efficiency. The API's polymorphic form is another key aspect. Different crystal forms can affect solubility, stability, and bioavailability. Similarly, the API's crystalline morphology impacts dissolution rates and overall performance. Cohesive and adhesive properties tell us how particles stick together or to surfaces, affecting processing and tablet formation. Electrostatic properties can cause particles to clump or repel each other, which is critical in handling powders smoothly. Hardness and plasticity indicate how brittle or malleable the materials are, influencing grinding and shaping processes. Viscosity, brittleness, and elasticity describe how materials respond to forces, whether they flow easily, crack, or deform elastically. All these factors are interconnected and vital for optimizing our size reduction process, ensuring we produce consistent, high-quality pharmaceutical products. Let's take a closer look at this example of milling. Here, the CMA, or critical material attribute, is the brittleness of the API itself. This is a key property that influences how the material behaves during processing. The CPP, or critical process parameter in this case, is the milling speed. Adjusting the speed can directly impact the efficiency and outcome of the milling process. Then we have the CQA, or critical quality attribute, which is the particle size distribution. Achieving the right particle size is crucial for ensuring consistent product quality. Now, the scientific insight behind this is quite interesting. When we increase the milling speed, we generally get finer particles, which can be beneficial for uniformity and dissolution. However, there's a balancing act because milling at excessively high speeds can generate too much heat. This heat isn't just a thermal issue. It can cause polymorphic changes in the API, which might alter its efficacy or stability. So, optimizing milling parameters isn't just about speed. It's about finding that sweet spot where we get the desired particle size without risking unwanted changes in the material's properties. This example ties back into our overall theme of process understanding. It's about controlling the process parameters carefully to ensure we meet product quality targets while maintaining stability and effectiveness. Let's take a closer look at the concept of the integrated relationship here. We see that CMA combined with CPP leads us to CQA. Now, what does that really mean? Well, CMA, which stands for particle size, directly influences the process. Think of it as the raw material characteristic that sets the stage. Then, CPP, or mill speed, affects how we process that material in real time. When we adjust mill speed, we're really influencing the particle size distribution, which is our CQA, or critical quality attribute. This chain of relationships highlights a key principle. Quality isn't something we test for after the fact. Instead, it's built into the process from the start. By controlling particle size and mill speed, we're proactively ensuring the final quality. This integrated approach emphasizes that quality is designed into each step, making our processes more reliable and efficient. It's a fundamental shift from testing quality at the end to embedding it throughout the manufacturing journey. So to wrap things up, let's talk about how CMA, CPP, and CQA are interconnected. These three elements are really the backbone of a robust development process. Each unit operation within our process has clearly defined inputs, controls, and outputs, which helps us maintain consistency and quality throughout the manufacturing. This structured approach is absolutely critical for ensuring the final product performs as intended. It also supports our quality by design principles and helps us stay compliant with regulatory expectations. When we understand and control these key aspects, we can build a more reliable, efficient, and compliant process. Ultimately, these connections reinforce the importance of a thorough, science-based approach to pharmaceutical development, making sure we deliver safe and effective products every time. For further support, please don't hesitate to reach out. We're here to help and ensure you have all the resources you need. If you have any questions or need additional information, feel free to contact us. Thank you so much for your time and attention today. We appreciate your engagement and look forward to assisting you further.